So I wanted to clarify a couple of things about these formulas for the Ricci curvature that I worked on last time. So the key player in this business is the canonical bundle of a complex manifold. So by definition, that's the bundle of N0 forms on M. And that's a complex line bundle because at a point I only have one choice of an N0 form up to a complex scale. So just the wedge product of the complex coordinate form. So that's a holomorphic line bundle. And what I was saying is that, okay, so element of the fiber, capital omega, is going to look like, at some point is going to look like a scalar multiple of the standard coordinate form. So now, if I'm assuming that I have a Kähler manifold and little omega is a Kähler form, then this gives me a natural way of measuring length in the fibers of the canonical bundle. So it gives me a Hermitian metric h sub omega on the canonical bundle. And h sub omega, so it's a quadratic function evaluated at a point in the fiber. That's just going to be basically the Hermitian square of omega. So that's n type n0, that's type 0n. So the whole thing is type nn, so it's just a volume form. If I normalize in this way, it's going to be real and non-negative definite. And then I just divide that by omega to the n. Now the main formula is that if I take the curvature form of this Hermitian metric on the canonical bundle, then I get the Ricci curvature of the underlying Kähler structure up to a minus sign that I forgot last time. That's kind of important if you're talking about Ricci curvature. It's positive or negative. So if I take the curvature form of the Hermitian metric associated with the scalar form, that's just going to be the Ricci curvature of the Riemannian metric associated with the Kähler form evaluated at Ju and V. So that's the main formula. And if I write out what that means in local coordinates, which is basically one way of actually proving the formula, to write it out in local coordinates and then compute with that. And what this is saying is that, so in local holomorphic coordinates, this is saying that Ricci of jk bar is minus d squared by dzk, dzj, dzk bar of log of the determinant of the metric tensor. So I'm using complex and anti-complex indices. So then I wanted to give you a couple more details about this problem of prescribing the Ricci curvature of a Kähler manifold, which by this formula is pretty much equivalent to prescribing the volume form of a Kähler manifold. So I just wanted to set up the equation that you need to solve. And I guess tomorrow and on Friday, I'm actually going to show you that the equation can always be solved so that we can prescribe the Ricci curvature of a Kähler metric. For example, to be identically 0. Okay, so by this formula, the Ricci curvature is minus the curvature form of a Hermitian metric on the canonical bundle, so that's the kind of thing I should start with. So that's a closed real 1-1 form. And this is what I would like the Ricci curvature of my Kähler metric to be. That's up to multiplying by I here. I want to find a Kähler metric whose Ricci curvature is given by this prescribed 1-1 form. So now by the Del-Bar lemma, because it's a curvature, it's a line bundle for Chern class of a line bundle, I know that rho is definitely the curvature form of some Hermitian metric on the line bundle. So I know that rho is actually omega sub h for some Hermitian metric h. The minus sign everywhere. Now what I do is I fix any Kähler metric omega 0 on M. That's sort of my initial guess that I want to improve. So that, the Ricci curvature of omega 0 is going to be something, and I want to improve omega 0 so that this Ricci curvature is equal to this thing, rho. So if I fix omega 0, then I'm going to have an associated Hermitian metric H sub omega 0 on the canonical bundle. So I want to relate that to this Hermitian metric H that I got from here. And I've got two Hermitian metrics on the same holomorphic line bundle, so they're going to differ by, a smooth positive function on the base. So I'm going to be able to write H sub omega 0 as e to the f times h. Where f is some real valued function. And this is of the difference in volume forms of my Kähler metrics that I need to account for. So the equation that I want to solve is omega 0 plus IDD bar u to the n equal to e to the minus f omega 0 to the n. So if I was able to find the potential u so that omega 0 corrected by delta bar of that potential has this volume form, so that the nth power is equal to e to the minus f times the original volume form, then I've precisely corrected the difference in volume forms, or the difference in the associated Hermitian Hermitian metrics on the canonical bundle. So if I take this guy, I mean this corrected Kähler form, if I take this to be omega, then it's actually going to be true that h sub omega is equal to h. So the Ricci curvature associated with omega is equal to the given form rho. Yeah.
May you explain again the previous, like h sub omega 0 is equal to the power f?
Yes. So I want the Ricci curvature to be rho. Okay. I know that rho is minus the curvature form of some Hermitian metric h on this line bundle. But that's a Hermitian fiber metric on the line bundle. Now I pick a random Kähler metric on the base. I take the associated Hermitian metric on the line bundle. This is some random Hermitian metric on the line bundle. So I'm actually going to be able to write the quotient as some positive function e to the f. And f is going to depend on omega naught in some random way. I have no idea what f is really.
You just want this to be positive, you don't care about exponent.
Yeah. I'm just taking log of the ratio of the two Hermitian metrics. So the Yau's big theorem is that I can actually solve. I mean, this is the complex Monge-Ampere equation. So if M is compact, So this condition here is a little bit like when you're trying to solve the Laplace equation, Laplace u equals f on a compact manifold. So you integrate, you have Laplace u equals f, and then you integrate both sides of the equation over the manifold, and you get that f has to have mean value 0. It's the same deal here. If you actually want to be able to solve this equation, then by integration by parts, you see that this condition needs to be satisfied. But, yeah? 0. Sorry. Yeah. You're taking the difference and you're integrating by parts. Get that this actually has to be 0. But the good thing is that you can always achieve that by changing f by an additive constant. But the good thing here is that h, this Hermitian metric, was only determined up to a multiplicative constant. So I can always change h by a multiplicative constant without changing the curvature, and that corresponds to changing f by an additive constant. So, I'm always in a situation where I can apply Yau's theorem. So h, this is unique only. Multiplication by a constant. Okay, and tomorrow and on Thursday I'm going to try and give you sort of the complete proof of Yau's theorem. But today I just wanted to try and give you some examples of what sort of geometry is hidden behind the theorem, and what sort of examples of metrics and Riemannian spaces you get as a result of the theorem, because it's just an abstract existence theorem, so it actually doesn't tell us anything about what these solutions look like. You just know that there's some smooth function solving this, So for example, if the canonical bundle is trivial, we're going to know that, there's sort of plenty of Ricci flat Kähler metrics on our complex manifold, but we have no idea what they actually look like. This is a completely abstract theorem. I was just trying, today I wanted to give you, a couple of concrete examples. You can actually see what kind of geometry is going on, these metrics. I guess it would have been lecture 8 on the syllabus, so that's some examples of Ricci flat spaces. I'm going to try and give you 3 examples. First one is actually still pretty abstract. So K3 surface. So say you start with a degree D complex surface, algebraic surface in P3. So 0 locus of a degree D polynomial. Then there's a pretty easy way of calculating the canonical bundle of this guy. So you use something that's called the adjunction formula. It's a pretty easy result, very useful. So adjunction formula tells you that the canonical bundle of M is the canonical bundle of P3 tensor the line bundle associated with M restricted to M. So these are line bundles on P3 and they restrict them to M. Now this guy here is O of minus 4. So that's a homework problem today. This guy here, I've just been assuming that the thing is a degree D complex surface, so this is just O of D. And then what Yau's theorem tells you is that if D is less than 4, you're going to have Kähler metrics of positive Ricci curvature. If D is greater than 4, you're going to have Kähler metrics of negative Ricci curvature. And if D is equal to 4, then you're going to be able to have Kähler metrics whose Ricci curvature is identically 0. Okay, so in particular, so if you have a quartic surface, degree 4 surface, it's going to have Ricci flat Kähler metrics, and this means a quartic surface is an example of a K3 surface. So compact complex surface. It's called K3. M, if and only if it's simply connected. So that's just there to rule out tori. And the canonical bundle is trivial. So for boring example would just be, tori C2 mod gamma with a flat metric. So we don't need Yau's theorem for that. Then examples like the quartic in P3 are sort of less trivial, and they're singled out by this condition that the fundamental group is 0. So I'm not assuming Kähler in that definition, even though you need Kähler to run Gauss' theorem, but it's actually known that these conditions automatically imply Kähler. There's something pretty interesting going on. There was noticed a long time ago by Kodaira and Spencer in the 50s or 60s, of long before anything like Gauss' theorem was proved, which is that the space of K3 surfaces is 20-dimensional. It's the space of all K3s. And in some local sense, if you have one K3, then the space of all neighboring K3s is 20-dimensional. But if you count so we saw that degree 4 surfaces in P3 are examples of K3s. Now, if you count on how many coefficients a degree 4 polynomial in P3 depends, then you see that you only get 19 parameters. I think this was puzzling people for a long time, because so this dimension was computed by abstract arguments. Sort of just abstractly, the dimension of the space should be 20. But if you want to, write down concrete examples, you only get a 19-dimensional family. You guys went to my class last week, so drew a similar picture for tori, and that's just basically the same story here. And this is something that I think Atiyah and Hitchin and these people noticed at some point in the 60s, that if Gauss' theorem was actually true, if it were true that K3 surfaces had Ricci-flat Kähler metrics, then I could have sort of explained this one missing direction. These P1s there. Reason is that if Mg is a Ricci-flat Kähler surface, then just in terms of the Riemannian metric, this means that the holonomy of the metric is contained in SU2. So Kähler means that the holonomy goes down from SO4 to U2, and Ricci-flat Kähler imposed that it goes down one more to SU2. And SU2 is a group, I can view that as a group of isometries of R4. So it's going to be complex linear isometries of R4, but the special kind, so it's actually quaternion linear. So if I view R4 as a space of quaternions, then these are just the quaternion linear isometries of R4. And if the holonomy group of a manifold lies in there, then this means by the holonomy principle that so each imaginary quaternion extends to a parallel complex structure on my manifold. So this means that I actually get parallel complex structures of the form, A times I plus B times J plus C times K, where A squared plus B squared plus C squared equals 1. Maybe, I is the one that I started with. And then I have this whole two-sphere of complex structure sort of given to me by the existence of the Ricci-flat metric and the holonomy principle, and those span a P1 in the moduli space that's sort of transverse to the space of quartics. So this is where these sort of exotic K3 surfaces come from, this missing direction in the space of K3s. So I need Gauss' theorem for that. Generically not. It's like there's it's the same picture as for tori, that you actually have like a countable dense union of divisors in this moduli space that correspond to K3s with a fixed polarization, like quartics in P3 or elliptic K3s or double sextics or something. Then you have this P1 cutting through, and there's sort of a countable dense set of points on the P1 that then corresponds to projective guys, and sort of the rest are irrational. Not projective, not polarized. They don't have any line bundles. For tori, with the same picture, it's just more explicit because the Ricci flat metric on a torus is just the obvious flat metrics. You can write down everything explicitly if you want. Don't need Gauss theorem for that. I'm going to give you two other examples of K3s, so not just quartics. Concrete examples of K3s. First one is the Coma surfaces. So these are examples where you can sort of begin to see what the Ricci flat metrics provided by Gauss theorem actually look like. Special K3 surfaces that are so explicit that you can actually make an educated guess as to what the Ricci flat metric should be. You start with a complex torus, C2 mod gamma. It's a torus. And then you pass to a quotient of that torus by a group action, but the group action is not going to be free, so it's going to have fixed points, so the quotient is a singular space. You take M naught prime, so this is M naught modded out by Z2. This is singular. And here Z2 just acts in the obvious way. So you have a coset Z plus gamma, coset of the lattice gamma, and you're sending that to the coset minus Z plus gamma. That's how Z2 acts. So you can see that the fixed points of the Z2 action are precisely those points on the torus, those points Z, so that 2 times Z lies in the lattice. So it's like the 2 division points, or the 2 torsion points on the torus, and there's 16 of them, so one in each coordinate direction, so it's 2 to the 4. So this is an action with 16 fixed points. And each of the singularities is just C2 modded out by plus minus 1. So I'm quotienting out C2 by the map that sends Z2 minus Z. So it's a local model at each of the 16 singular points of this guy. And then you want to resolve these singularities by some kind of blowing up. And so the way to do that is to realize that, first of all, there's a more algebraic way of realizing this quotient. So you have a map, one-to-one map from this quotient into C3, and the image is going to be a singular algebraic surface in C3, so that's a surface Z squared equals XY. A one-to-one holomorphic map there. And what does the map do? It just, it sends an equivalence class of vectors modulo plus and minus 1 to the triple. This is in C3. U squared, V squared, and UV. So So I've realized this singularity as a singularity of an affine surface in C3. So that surface is smooth except at the origin. That's the surface I put on one of the homework problems last week to show you how to actually construct a resolution of that surface by blowing up the origin in C3. So the upshot of that homework problem was that this is my singularity. So this is z squared equals xy. That's my singular surface. So the cross section here is just RP3. So that's the 3-sphere modded out by plus minus 1. And then I can sort of resolve that by sticking in a copy of P1. So I'm not changing anything away from the origin, I'm just replacing the singularity at the origin by a holomorphic copy of P1. That's the upshot of that problem. And actually this space here, so the smooth surface that I replaced my singular surface with, this is actually biholomorphic to the total space of P1 of minus 2, total space of this line bundle, and that's just the canonical bundle of P1. Now it's a general principle that whenever I have a complex, when I have any complex manifold, then so the total space of the canonical bundle has trivial canonical bundle. So this is like in symplectic geometry when you're saying that the cotangent bundle of a real manifold always has a symplectic form. The same way the total space of the canonical bundle sort of has a nowhere vanishing sort of tautological top degree holomorphic form. You see that we're in good shape. So, so we've got this torus that we modded out by this group action that has a bunch of fixed points, creating singularities of the quotient. So we can resolve each of the singularities of the quotient by this process. But so if the smooth space that we're replacing the singularities by is actually a complex manifold with trivial canonical bundle. We've kept the triviality of the canonical bundle there, and sort of on the main part of the quotient where I don't have any singular points, so away from these 16 points, I had a torus, which is trivial canonical bundle anyway, and so the C2 action preserves the triviality of the canonical bundle. So away from the fixed points, I have trivial canonical bundle, and I resolve the singularities of the quotient in such a way that the canonical bundle stays trivial there. So if I do that on all of the 16 points, I'm going to get a compact complex surface with trivial canonical bundle, and it's not hard to see that that's actually simply connected despite coming from a torus in the first place. So that's going to be a K3. But sort of a K3 that's built up from simple pieces. From these guys, a total space of KP1 and a torus. And then, so here, I'll give you another example in similar spirit. Let's slightly more complicated. So if you start with a rational elliptic surface, guys that are introduced on Monday. So you start with a pencil of cubic curves in the plane. So you have F, G, cubic curves in the plane intersecting in 9 points. And then you're looking at the family of cubics passing through these 9 points. So SF plus TG equal to 0, where S and T ranges over P1. Then if I blow up the plane in these 9 points, I'm going to get this rational elliptic surface that has a fibration over P1. The fibration P1 on the base, and the fibering map is just the ratio of S and T. And the generic fiber is a smooth elliptic curve, so that's a torus. And then there's a bunch of singular fibers as well. So now what I can do with this, I can take 2 copies of a rational elliptic surface and glue them together. That's what's called taking a fiber sum. What this means is you take a rational elliptic surface and you cut out one of the smooth fibers. So you take one of these tori, just a single one, and you remove that. So you've punched a hole in your space, and now what you do is that you open up this hole to a cylindrical end. So it's like you're removing this one point on the base. So you've punctured the base in one point, and then you're opening up the puncture to a cylinder. You stretch that to a cylinder. Across the whole thing with a torus. So what you're going to see is this picture that you have going to see a cylindrical end that's just R cross S1 cross T2. And then take 2 of these guys. And you stick them together by their ends. It certainly works topologically, and the result that you're going to get is a smooth 4 manifold, a smooth compact 4 manifold that's diffeomorphic to K3, but it actually works, even though it doesn't look like it, it works in the holomorphic category as well. So you're actually going to get a compact, complex surface, and that's a K3 surface. So it's biholomorphic to K3, so it's trivial canonical bundle. So now I want to talk about the Komar surface in the first place. So we've sort of assembled a K3 from simpler pieces. And I want to show you how that actually helps understanding the Ricci flat metric on K3 that's given to us by Yau's theorem. Because the idea is that, sort of on the body of this Komar surface, that's basically just a torus modulo Z2. I have a flat metric that's Ricci flat. Now, if I could put Ricci flat metrics on these guys, these plumbing fixtures that I use to resolve the singularities as these total spaces of KP1. If I had Ricci flat metrics on those guys, I could try to glue them together with a Ricci flat metric on this guy M0 prime. So for the obvious flat metric on there, and try and that way approximate the Ricci flat metric on the K3 surface. And there's some hope because these guys have a lot of symmetry. They have rotational symmetry. There's hope that I'm actually going to be able to write down a Ricci flat metric on these guys explicitly using the symmetry. So if these explicit pieces, hopefully with explicit Ricci flat metrics, and then I'm hoping that if I can glue together these Ricci flat metrics, I'm going to create something that's approximately Ricci flat on the K3 surface. So hopefully that's going to be a good approximation to what the Ricci flat metric of Yau's theorem actually looks like. Let's see. It's going to be the second example. It's, Gucci, Hansen, and Stenzel metrics. So we have this cone C2 mod plus minus 1, and we saw that this is isomorphic to a singular surface C squared equals xy in C3 via the map that sends uv to this vector u squared v squared uv. Okay, so now I'm going to introduce a family of surfaces in C3. So m sub t, and t is a family parameter, and that's going to be x squared plus y squared plus z squared equals t. And then if you take m naught, so if you set the parameter equal to 0, I mean, if t is different from 0, then that's actually going to be a smooth surface in C3. If you set t equal to 0, you get m naught. That's something that has one singular point at the origin, an isolated singular point, and it's actually isomorphic to this guy that we've been working with over there. So these guys are actually isomorphic. It's pretty easy to see. So what you do is you make a linear change of coordinates. Just for the rest of this example, I prefer to use these coordinates where the surface can be written in this way as a sum of 3 squares. Right here, yeah. So you have this family MT. If you set t equal to 0, you get m naught, and I'm saying that m naught is actually isomorphic to this guy. Yeah. And it's pretty easy to see because you have x times y here. No, you just replace the x by an x plus iy, and you replace the y by an x minus iy, then this is just going to become like x squared plus y squared. So it's just a linear change of coordinates. So this is m naught, just a different way of writing m naught. So then you have this picture here. Here's m naught. That's my cone. So I'm drawing it with two ends because it makes a picture nicer, but really it's a cone with one end. It's a quotient of C2. So there's only one non-compact end. This is C2. C2 modulo plus minus 1 in disguise. Now on one hand, I have this one parameter family m sub t that's somehow converging to this guy as t goes to 0. So m sub t. And on the other hand, I have this construction over there that blows up the origin. This is the blowdown map. And on here, this is the total space of KP1. So there's a P1 in here as a zero section the canonical bundle. So we've got this sort of discrete process of resolving the singularity. You have this continuous process of deforming towards the singularities from some smooth manifolds. So that's a basic example of a deformation of complex manifolds. You know, what's really remarkable about this example is that topologically, both of these ways of smoothing out the singularity of the cone are completely equivalent. So the M sub t's are actually diffeomorphic to the sky here. So this is the canonical bundle on P1. That's O of minus 2. That's the same thing as the cotangent bundle of P1 as a holomorphic line bundle. And it's a very nice exercise to check that these surfaces M sub t, for t different from 0, are actually diffeomorphic to the tangent or cotangent bundle of S2. So M sub t. So what's going on is that you actually have this cycle here. It's a topological S2, and the thing is diffeomorphic to a vector bundle over that 0 section. But it's, in a way, topologically it's the same S2 over here, but from the point of view of the complex structure, they're completely different. Because this is a P1, this is a compact complex curve. And this guy here is an affine surface. So it lives in C3, and C3 doesn't contain any compact complex cycles. So this guy is a topological S2, but it's not a holomorphic S2. It's not a complex submanifold. It's actually a Lagrangian. It's of the extreme opposite of complex. So the 0 section of TS2 is a Lagrangian surface. So meaning that if you take the Kähler form of C3 and restrict it to S, then as opposed to the area form, you're just going to get 0 identically. So that's S here. So what I'm claiming is that there's a metric picture here as well. So there exist complete Ricci-flat Kähler metrics. On M sub t and on this other guy, the resolution, the blow up, M0 hat. So they're asymptotic to the cone at infinity. And they're isometric as Riemannian metrics. And so what I want to do here is I want to turn these topological pictures into metric pictures. And I'm claiming that there actually exist explicit Ricci-flat Kähler metrics on both of these guys, M sub t and M0 hat. They sort of, I mean, C2 mod plus minus 1 is a cone. I mean, C2 has a flat metric. The flat metric passes down to the quotient. So that's a flat cone metric. It's just isometric to the cone over RP3 with its round metric. Now I'm claiming that on these guys there actually exist Riemannian metrics asymptotic to this cone at infinity that are precisely Ricci flat, and they're actually Kähler with respect to the given complex structures. And moreover, I'm saying that it's not only true that these guys are actually diffeomorphic, so both the tangent bundles of S2. It's actually true that with these Ricci flat metrics, they're going to be isometric. So it's the same Riemannian metric up to diffeomorphism, but as Kähler manifolds, they are different because it's just because this guy here is completely different as a complex manifold from this guy there, because of this two-sphere in here is a complex two-sphere on the right, and it's a Lagrangian two-sphere on the left. So the same topological manifold, the same Ricci-flat Riemannian metric, but I have two different parallel complex structures with respect to which the zero section behaves completely differently. And that's sort of, again, the quaternions showing up. This is like I and J or J and K, like parallel complex structures given by different quaternions. So the way that you actually compute formulas for these Ricci-flat metrics, well, that's a highly recommended exercise if you have the time. Sort of on M sub t. So this picture, the metric is called Stenzel's metric. So if the ansatz that you're making is you're trying to find a radially symmetric solution, and this is why I chose these coordinates, because in these coordinates you can see that the thing has a huge symmetry group a priori. It has SO3 symmetry. You can just let SO3 act on this guy by acting on this coordinate vector, and it's going to leave the equation invariant. So it makes sense to look for a Ricci-flat metric that's also invariant under this SO3 symmetry. And what I can try to do is to write omega as delta bar of some potential phi, and that's only going to depend on rho, where rho is the Euclidean radius. So that's a reasonable thing to try and do, because these M sub t's are affine varieties, so it's perfectly reasonable to think that a given Kähler form actually has a global potential. I mean, that's true on Cn. So if you think this through, if you sort of set up the complex Mohr-Ampère equation that needs to be solved to get a Ricci-flat metric of this form, you're going to see that the Mohr-Ampère equation actually reduces to a second order ODE in this radial variable rho. So because of the symmetry, you reduce the PDE to an ODE. And the explicit solution is actually pretty simple. So what you're going to find is that this potential phi of rho is just given by the square root of rho plus 1. Rho plus t on mt. And that's sort of a nice exercise to see that if you compose all these isomorphisms from C2 mod plus minus 1 to the surface z squared equals xy to the surface m naught. So that's the thing with these UV coordinates, and that's this linear change of coordinates. So on here you have the scalar potential square root of rho. So when you set t equal to 0, you just get square root of rho. So if you pull that back on these two isomorphisms, then here what you're going to get is just the Euclidean Kähler potential mod u squared plus mod v squared. So in this picture, square root of rho, which is the value of this potential at time 0, is just the Euclidean Kähler potential sort of pushed forward on all of these isomorphisms. So that really means that at time 0 on the surface M0, you're just going to get the quotient of the Euclidean metric by plus minus 1. And when t is small, you get something that's sort of a smoothed out version of that. That actually solves the Monge-Ampere equation. And then on this other guy, on this blow up, on the cotangent bundle of P1, you can do a similar thing. But the formulas are going to be much more complicated, and there's a reason for that. So you're trying to do the same thing. You're trying to use the symmetries of the problem to reduce the Monge-Ampere equation to an ODE that you hope to be able to solve explicitly. So what you're saying is that, well, M0 hat minus this P1, that's just biholomorphic to C2 minus, so C2 minus the origin, modded out by plus minus 1. So away from this P1, I haven't actually done anything to my complex space. Okay, so on here I have these holomorphic coordinates u and v. So what I'm going to try to do is try to solve a complex Monge-Ampere for a radially symmetric metric omega of the form IDD bar. Phi of t, where t is now just the Euclidean radius squared. So again, you're reducing the problem to an ODE, to like a one independent variable problem. It's just that in this case, the solution is much more complicated. It's still explicit, but not particularly nice anymore. So you can actually do that. What you're going to get. You're going to get a solution. Maybe I shouldn't be calling this T. So, anyway, so what you're going to get is phi of t. It's going to be cosh t plus log tang of t of x. Need to substitute log tang of x over 2, where t is sinh x. It's a solution in this picture. And what you can see here is that the solution over here was just a perfectly nice smooth function on my manifold, globally defined and smooth. And here you're seeing that this guy has a logarithmic divergence at the origin. It has to be that way, because we know that if we take, if you take del bar of log of some distance function, basically what we're going to get is like a delta function supported on whatever we're taking the distance from, more or less. And so that's precisely the CP1 that I've glued in. So it's this P1 here. And del bar of this log term is precisely going to give me like a delta function, like the current of integration supported on this P1. And this kind of had to be there because this is a holomorphic P1. That's actually a complex submanifold. So del bar of this is a delta function. Supported on the P1. So in other words, I'm actually going to, in this picture, I'm going to be able to write my Ricci flat Kähler metric as del bar of some potential, but the potential is only defined away from this holomorphic P1. It actually has a logarithmic singularity along that P1, and that has to be there because that's a holomorphic P1, that's a complex submanifold. And then del bar of the log term is sort of Poincare dual in the sense of currents to this complex submanifold. And then it's actually true, and it's going to follow from sort of the proof of Yau's theorem that I'm going to show you. That if you take these models and glue them together with a flat metric on this torus, you're going to get something approximate Ricci flat. And so if the honest Ricci flat metric produced by Yau's theorem is going to be close to this approximation. So if you have a pretty good understanding of these metrics, then at least approximately you're going to get a pretty good understanding of what the solution to Yau's theorem, the Ricci flat metric, looks like in this case. Okay, and I'll do one more explicit example tomorrow and then go into the proof of Yau's theorem.